Hello, everyone, and welcome back. We are still working with Geoboards, and our part 5 session today, we're going to look at angles, parallel, and perpendicular lines. And so this would be a place we could start, or this could be a place that we could use for formative assessment to see how they might be identifying pieces that we've done. So if we've already taught them about angles, we've been using, if you're in grade 3, you've been using a right angle as your tool to make a decision about whether an angle is larger than 90 degrees, smaller than 90 degrees, because they don't know how to use a protractor yet. Or if you're in grade 4 where they are learning how to do a protractor. So depending on what you've done with them so far, or if this is your starting point, you're going to have to adjust it accordingly. And then the same with parallel and perpendicular lines. If you talked about those in the attributes of the different shapes when you were doing that with shapes, then we're going to use the Geoboard today to verify that they can identify what a parallel line is, describe it to us. Can they find instances where there are parallel lines on the Geoboard that we've created, or perpendicular lines, or both, whichever the case may be. So we're going to start, and I've done all of my Geoboards a little bit ahead of time today because we have so many of them that I want to just look at. But again, you can use any one of those as an idea or a model to move forward. So here I have 3 different angles, and I'm going to go back to what I just said previously. If I was in grade 3, they don't know how to measure with a protractor. So what we have them do is cut out something that has a right angle in them. So we give them a square, and we ask them to compare things in the room, things that they see every day. What has a right angle and what doesn't? What has an angle that's larger than 90 degrees? This one goes well beyond that. Which one has one that is smaller than? Well, this one's only going up to here. It's quite a bit smaller than the 90-degree angle. So that's what they use in grade 3. But in grade 4, they could easily put their protractor, their 0 here, and then go ahead and measure. So either they're reinforcing what you've already done, or now we're going to use that as our tool. I would say if you're going to do a protractor, you probably want to do that with nice, beautiful lines on a piece of paper and start with that. And then once they've mastered that, then they can come here and they'll feel quite comfortable with it. So we start with a right angle. That's where the students start to learn what a right angle is, just by measuring this way. And then they learn that anything that is larger than a 90-degree angle, in this case, one that looks like this, is called an obtuse angle. And if the angle had gone straight across, it's called a straight angle. It forms a straight line. So we talk about what degree measures each of those are, and they learn those pieces. And then, of course, the last one was the acute angle. And the whole idea is for them to be able to identify things in everyday life that have these different size angles in them. That should be a first starting point. Let them explore the classroom, walk in the hallway. You know, can you find me 5 obtuse angles? Can you find me 5 right angles, et cetera, et cetera. And then they make a list of it and come back, and you can make the list on the board and compare all the right angles that everybody found. Same thing with acute. But we also want to move this then when we get into discussions about triangles, different kinds of triangles. So let's just grab a new board, keeping in mind that we talked about the angles. And here I have 3 triangles already done on the board. Now, again, I could have these on a slide and ask them to recreate it in front of them, which I would actually, because I really feel that having it in front of their own and making their own is going to be much more memorable for them. And then I might even just say, you know, what do you notice about any of these triangles? You know, commonly, yeah, they have three angles in them, 3 sides. Do they all look the same? No. Are there things that you think are the same in them? So, you know, they might take if they're grade 3, they might take this and, okay, that's acute, that's acute, that's acute. So all 3 angles here were acute angles. This one had a right angle in it, okay? And then it had 2 that were acute. So having them just do that, if they have their protractor, they could use their protractor. And then we would also say, you know, what do you notice about the sides? In this one, all of the sides are different lengths. I don't have to have a ruler. I can just see that this one went up to here, Okay, and it was about that much long. That one, oh, it's a whole side long. This one's even shorter. So this one has 3 different sides. So we'd like them to know the names of the triangles based on the angles that are in there, and then also by the lengths of their sides. So when 3 sides are not the same, this is called a scalene triangle. When 3 angles are like this, and we'll talk about that in just a minute, and one of them happens to be bigger than 90, this is the obtuse one right here, this is called an obtuse triangle. You can't, and that's a question I ask students, how many obtuse angles can you have in a triangle? And you'll get lots of different answers. Again, it depends on what you've connected for them when you did your shapes. When you make a square, how many right angles do you have? 4. How many angles, total degrees, are there in a square? 360. If a triangle is half of a square, then what's the maximum angles that you would have in a triangle? So 180. So could I have more than one angle that's larger than 90 and the other 2 smaller than 90? Could I have 2 that are like 91 and 93? And the answer is no, because it can't be larger than 180. So in this one, I have a right angle, and so this would be called a right angle triangle, but the lengths on this side and this side are identical. This one is longer. So 2 identical length sides are called isosceles triangles. And here, when they measure and find out, they will notice that all 3 angles are the same. So again, I can tell them, but I'm not. I'm going to ask them if I can only have 180 degrees in a triangle, then what would each angle be if they're all the same? So dividing 180 by 3 to get 60. And in this case, if they measured the sides, they will find that they are all the same length. So a rule that not often gets discussed, but 3 different angles were in this obtuse angle triangle. That's because I have 3 unique angles. I will also have 3 unique sides. The number of angles equals the same number of sides in a triangle. So if I have 2 sides that are the same, I will have 2 angles that are the same. These 2 angles just happen to be the same. If this is 90 and these 2 sides are the same, these 2 will be identical angles and they'll be 45. Not every right angle triangle will have a 45 and 45. But because these 2 sides were the same, isosceles, then the 2 angles are identical. And here I had 3 angles that were the same, so therefore 3 sides are the same. So equilateral refers to the sides, equiangular refers to the angles. So again, we're making connections with something as simple as starting with where I did in grade 3 to using my protractor to identifying. I should be able to visualize and just name for you. That's an acute angle, that's an obtuse angle, that's a right angle. So we want them to be able to make those connections as they go through. Okay, so then just adding a little bit more to the plate. For those of you that are working on similar and congruent, I can create that as well on my Geoboard. So congruent means they are identical in every way. It's like cutting it out and laying it over top of one another, and there's no overlap, there's nothing missing. These 2 triangles here are congruent. If I took this one and lifted it up and put it over here, they would be a perfect fit. A bit of a shadow there, I see. At the top, I have a right angle triangle, and then I have a smaller one that's built inside of it. And this one in here is really the same, exactly the same as the big one, just a smaller version of it. So these are called similar triangles. They are the same shape. They have the same angle measures, just their sides will be different lengths because they're like miniature versions of the same thing. And how do I know they're similar? These lines, and when they are similar, these lines here will be parallel. If for some reason this one went up like this, okay, that definitely doesn't look like it's going to be similar anymore. So we want to ensure students understand how that works and that those are going to be the same. So now I could ask the question, where do I see parallel lines? Where do I see perpendicular lines? So again, you might want to refresh their memory about what are perpendicular, or ask them rather than telling them, what is a perpendicular line? So it's the two lines that form a right angle. So again, we want them to look around the room. Where do they see parallel? Where do they see perpendicular? What do I know about parallel lines? I know that they're never, ever going to meet. Can they think of a real world example? Railroad tracks, that's a good one. Those aren't going to meet, and if they do, we're in trouble. So if we were to go back to some of the shapes that we were working on earlier, and it's a good time to revisit them. These are your quadrilaterals, and we unpack some of these again in grade 4 and 5. So quadrilaterals are any four-sided figure. Now, they can come in a lot of different shapes, and we've seen that. We've seen squares, we've seen rectangles, we see the trapezoid, and trapezoids tend to have two sides that are parallel, but they don't have to be the same necessarily. Here's an example. This is also a quadrilateral, even though it doesn't look like it should be. So all of these are examples, but now this is a perfect one for me to say, show me where the parallel lines are, show me where the perpendicular lines are. And can you identify them? And how do I know that they are parallel? Well, these two sides here, if they were to keep going indefinitely, are never going to meet. I could take rulers and lay them on top. There's nothing they can do that's going to make them meet. I could do the same thing with the top and the base. And then what about this one? You know, a lot of times we'll say, well, is that a quadrilateral? Yes, it is. Is it does it have a name? Well, it could be a rhombus. Some people say that a rhombus has to have different angles in it, and it doesn't. This is an example of a rhombus, but if I have a diamond that's been squished in a little bit, that's still a rhombus. But here, really what I've done is I took my square, let's do it this way. I just took a square and I turned it on its side. So these are, in fact, right angles in this particular case. So again, students, where do I find right angles? Do I see any examples on my page of an obtuse angle? Where would you see them? Oh, I see one right here. I see another one right here. Do we see any acute angles? Well, I see one right here. I see one right there. I see one right here. Do I see right angles? So just doing that. And then I would say, can you make a funny shape? It can make it different this time. Make it have 5 sides where one of the angles is a right angle. And it's possible that you call something out that they just can't make, but just letting them try is a good. So just giving them opportunities to demonstrate for you. Can they make a shape that does have parallel sides in it? Can they make a shape that has perpendicular lines in it where then they're going to have a right angle? But we're not going to say that. I just want where your shape has perpendicular lines. So just giving them the opportunity to play a little bit and be creative. And to be honest, I will be remiss if I didn't say that at some point when you pull these out, even if it's only for 3 minutes, you need to be able to say, you have 3 minutes to make a design of your own. And maybe you say, make a design of your own that has parallel and perpendicular in it, and just let them go to town and have some fun. Because you've got a lot of different color possibilities here, and it's pretty engaging, and it's pretty hard not to want to use your creativity. So whatever you've worked with them on that today or in that particular lesson, just give them that 3 or 5 minutes to say, all right, you make me a design, a picture of your choice, what it looks like, but it must have these in them. And then they can go from there. So I hope that gives you some ideas of things that you can do other than just create the shapes. It goes well beyond that. And you have to leverage it at any time. And I'll be honest with you that I'd be doing arrays here too. Like I'd be saying, oh, by the way, what's the value of this? What's the math fact that's there? And what's its value? What's the value of this? If they have to turn it around, turn it. And if they've already done their trapezoids, then what's the area of that trapezoid? So I don't have to be in geometry and ignore number. I don't have to be in number not to talk about geometry. So grab the teachable moments at any time that you have them. And that's just quick review then for them at the same time. All right. Thanks very much, everyone.